Welcome to our deep dive into the fascinating world of physics. Fasten your seatbelts because we're about to embark on a cosmic journey through the mind-blowing realities governing our universe. Today, we're uncovering 15 mind-blowing facts about quantum mechanics, string theory, and thermodynamics. These aren't just abstract theories, they're the fundamental laws shaping the reality we experience every second. So get ready to expand your minds and challenge your perceptions of the universe. Imagine two particles, light years apart, linked in a way that defies our classical understanding of space and time. That's quantum entanglement. When you measure the state of one particle, the other instantly knows and changes its state accordingly. Einstein famously called this spooky action at a distance. It's like they're connected by an invisible thread, communicating faster than the speed of light. This bizarre phenomenon has puzzled physicists for decades, and has huge implications for the future of quantum computing and communication. Imagine the universe not as we see it, but on a much smaller scale. So small that even atoms are like giant galaxies. String theory proposes that everything in the universe, from the smallest particles to the most massive black holes, is made up of tiny, vibrating strings. These strings are so minuscule that they're far beyond our current ability to observe directly. Each vibration of a string is like a note on a cosmic guitar, and the symphony of these vibrations makes up the universe as we know it. It's a mind-bending concept that attempts to unify all the fundamental forces of nature. In the quantum world, certainty is an illusion. The Heisenberg uncertainty principle states that you can't simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely you measure one, the fuzzier the other becomes. It's like trying to nail down a shadow. The act of pinning it down changes its shape. This principle highlights the inherent fuzziness of the quantum world and challenges our classical intuitions about how reality behaves. Chapter 4. Thermodynamics, the flow of energy, and the arrow of time. Thermodynamics is the study of how energy flows and transforms in physical systems. It's all about heat, work, and the fascinating interplay between them. This branch of physics governs everything from the engines in our cars to the processes that power the sun. At its heart lies the concept of entropy, a measure of disorder or randomness. The more disordered a system, the higher its entropy. Chapter 5. Quantum tunneling through the looking glass. Imagine throwing a ball at a wall. In the classical world, it would bounce back, right? But in the quantum realm, there's a chance it could pass right through. This is quantum tunneling, the ability of particles to pass through energy barriers that they shouldn't be able to overcome classically. It's like a ghost slipping through a solid wall. This counterintuitive phenomenon is crucial for many technologies, including transistors and even the nuclear fusion that powers stars. Chapter 6. The multiverse. Are we just one bubble in a cosmic bath? The multiverse theory is one of the most mind-boggling ideas in modern physics. It suggests that our universe, vast as it is, might be just one of many universes coexisting like bubbles in a cosmic bath. Each universe could have its own set of physical laws and constants leading to an infinite variety of realities. While still speculative, the multiverse theory is supported by some interpretations of quantum mechanics and cosmology. Chapter 7. Entropy is like the universe's messy roommate, constantly increasing disorder. This fundamental law of thermodynamics states that the total entropy of an isolated system can only increase over time. Think about it. It's much easier to break a glass than to put it back together. This relentless march towards disorder has profound implications for the fate of the universe. Chapter 8. Light. Is it a wave or a stream of particles? The answer: both. This mind-bending concept, known as wave-particle duality, is a cornerstone of quantum mechanics. Light and matter can exhibit both wave-like and particle-like behavior, depending on how we observe them. It's like a coin that can land on both heads and tails at the same time, a profound demonstration of the weirdness of the quantum world. Chapter 9. In the world of quantum mechanics, size definitely matters, and nothing underscores this more than the Planck constant. This fundamental constant, denoted by the letter h, is incredibly small, representing the smallest possible unit of energy that can be exchanged in a quantum interaction. It's like the pixel size of the universe, setting a fundamental limit on how finely we can measure energy and time. Without the Planck constant, there would be no quantum mechanics, and our understanding of the universe would be fundamentally different. Chapter 10, Blackbody Radiation, the glow of quantum weirdness. A black body is an idealized object that absorbs all electromagnetic radiation that falls upon it. But here's the catch. When heated, it emits radiation as well. With a spectrum that classical physics couldn't explain, Planck's solution to this ultraviolet catastrophe marked the birth of quantum mechanics. Chapter 11. The second law of thermodynamics, the arrow of time points towards disorder. The second law of thermodynamics states that the entropy of an isolated system always increases over time. It's like a cosmic one-way street. Once entropy increases, there's no going back. This law explains why coffee cools down, why ice melts, and why it's impossible to build a perpetual motion machine. Chapter 12. Quantum superposition. Schrödinger's cat is both alive and dead. In the quantum world, objects don't have to be in one state or another. They can be in multiple states simultaneously. This is quantum superposition, famously illustrated by Schrödinger's cat thought experiment. Imagine a cat in a box with a device that has a 50% chance of killing it. Until we open the box, the cat is both alive and dead, a mind-bending concept that highlights the probabilistic nature of quantum mechanics. The holographic principle is one of the most mind-blowing ideas to come out of theoretical physics. It suggests that our three-dimensional universe could be a holographic projection of information encoded on a distant two-dimensional surface. Just like a hologram can encode a three-dimensional image on a two-dimensional surface, our universe's information might be stored on a cosmic horizon far, far away. Absolute zero, or 0 Kelvin, which is negative 273.15 degrees Celsius, is the lowest possible temperature where all molecular motion theoretically stops. The third law of thermodynamics states that it's impossible to reach absolute zero through any finite number of thermodynamic processes. It's like a cosmic speed limit. You can get arbitrarily close, but you can never quite reach it. Quantum systems are incredibly delicate. Quantum decoherence is the process by which these systems lose their quantum properties and transition to the classical world we're familiar with. It's like a wave collapsing into a particle when we try to measure it. This phenomenon is a major obstacle in building large-scale quantum computers. Thanks for joining us on this journey through the wonders of physics. We've only scratched the surface of these mind-blowing concepts, and there's still so much more to explore in the vast universe of knowledge. Don't forget to like, subscribe, and hit the bell icon for more fascinating science content. Keep questioning, keep learning, and keep looking up at the stars.